Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. So today we're going to continue our class with discussion on multivariable calculus. Okay, so let me just get the slides on. And functions of several variables. So we're gonna basically discuss how we can form a function that contains more than the two variables. So far, we have only been dealing with the function of with two variables, one dependent variable y and one independent variable x. Okay. Um, so besides that, we can extend the concept of function to include more variables. Now, if the domain of a function is a set of ordered pairs, so instead of just one variable, we have a pair of variables, ordered pairs of variables, then it becomes a function of two independent variables. So an equation of the form z equals f of x and y, where f of x and y is an algebraic expression in the variables x and y. So we have two variables x and y. So these two, okay, independent variables. So if we express our function in this form, then it becomes a function of two independent variables. Our function f, okay, f of x and y is a function of two independent variables x and y. So x and y are known as independent variables, while z is known as the dependent variable. The domain is the set of all ordered pairs, okay, all these couple x and y, okay, x and y, such that the output of the function becomes a real number, while the set of all corresponding values of f of x and y, the function, the output, is the range of the function. Okay. Now, similar definitions for functions of three or more independent variables can also be made, but that will be outside the coverage of this course. Okay, so let's just look at this example. So now instead of one variable, we have two variables. So this is a cost function because in reality, usually cost function involve more than one input, right? I mean, in economic, usually we have labor and capital. Okay, labor and capital, the wage for labor and the interest paid for the capital. So let's say this is our cost function, which consists of two independent variables or two input x and y. 700 plus 70x plus 100y. Now we want to know what is the cost when we use 10x and 5y. So how do we do this? So the solution would simply be to replace. Okay, so we shall replace x with 10 and y with 5 in the function. So we have 700 plus 70x. So what is our x? 10 plus 100 y. What is y? 5. So we have 700 plus 700 plus 500. And this becomes 1,900. So this would be our total cost. Okay, our total cost. As simple as this. Okay, example 2, I'm going to leave this to you. What you need to do, you simply need to replace, substitute all the independent variables x, y, and z with this. So this is a function of three independent variables. We have three independent variables. Okay, I'm going to leave this example to you as well. Okay, let's go through it. Make sure you know how to find the profit, okay, function when you are given a revenue and a cost function of two goods. Okay, of two goods. I'm just gonna this would be for your own reading as well, but these examples they are not really I mean, I'm not going to basically ask you to check on this, except this. The area would be something that will be applicable. Okay, applicable. Others are also applicable, but I'm just going to leave this for your own reading. Okay, for your own reading. Let's go straight away to example. Okay, this example, the Cobb-Douglas production function. So in economics, we have a special type. We have several special types of production function. This production function, so f of x and y, this would be the output. okay, the output production function, which depends on two inputs, x and y. Okay, x and y. So if it is in this form, k, okay, which is a positive constant, and then we have x, which is the input to the power of n, and y to the power of n. Okay, so this is what we call as the Cobb-Douglas production function. Okay, where x, we have the input to the power of a constant. Okay, we have two inputs, and each of them is to the power of a positive constant, where m plus n equals 1. Okay, for 1. And this is usually applicable when we have two inputs, right? I mean, this can be labor and capital, this can be tools or machinery, it can be buildings, and so on. When we have more than one input. Okay, so the Cobb-Douglas production function are also used to describe the productivity, okay, of a single industry or a group of industries producing the same product, or even an entire economy, okay, of or in an entire country. Okay, so let's have a look at this example. So let's say, so this is a product, a Cobb-Douglas production function where we have 10 to the n, 10 multiplied with x to the power of 0.2, y to the power of 0.8. And we know 0.2 plus 0.8 is 1, right? So this is a Cobb-Douglas, okay? Cobb-Douglas production function. Now, if the company uses 3,000 units, so where x is, so x is labor and y is capital. So 3,000 labor, 1,000 capital, how many units of steel will be produced? So how do we do this? We simply need to substitute. So now we have x equals 3,000 and y equals 1,000. Equals 10 multiplied with 3,000 to the power of 0.2, and then multiply with 1,000 to the power of 0.8. Okay, so how do we do this? Simply make use of your calculator. Where is my calculator? Calculator is here. So we have, let's see here. We have 3,000 to the power of, for this calculator, I need to have a scientific calculator. Okay, so we have 3,000 to the power of to the power of 0.2 volts multiply with, can I sometimes you should be able to use so this is multiply with 1,000 power of 0.8, and then multiply by 10 equals to something around 12,000, right? Oops. So where is my calculator? This now is so 12,000. Okay, I need to get back to my slides here. Okay, so yeah, more or less this number, right? 12,547 from our calculator. Okay, so that would be the example of how we apply this function with two independent variables. Okay, so please make sure you familiarize yourself. Okay, how to be careful with regard to the operation, plus, minus, multiplication, division, when you are evaluating a function of two independent variables. And this is just to show you how the graph would look like. So if you are given a graph with two independent variables, so now we have three dimensional coordinate system instead of just x and y. So now we have z. So it will be a 3D, a 3D. So this is an example how do we locate, okay, a coordinate with of a function with two independent variables. So altogether we have going to have three variables, right? Two independent and one dependent. Okay, so 3D. So if we have this z equals x squared plus y squared, how does it look like? It's going to be a parabola. Okay, a parabola. This is a parabola. So something that looks like a parabola. It is a 3D. Okay, 3D. Okay. Um, just to explore, okay, a bit of this. I mean, if you remember later on, okay, we're going to do some kind of test, but if you just recall the second derivative test, remember the one with the one variable. So if we have f of x positive, like in this case, because this is positive, right? I mean, just to share you the concept. So if we have a positive, it should be a smiling face, isn't it? So in this case, that's why our parabola with the 3D, if this is, later on, we're going to see how we're going to do the second derivative test when we have more than one variable, okay? But it's just that the same concept applies here. So since this is positive, it will be concave up, right? Concave up, and because of that, our parabola shaped like this, the 3D dimension. So now you have a kind of a real cup, okay? Rather than a 2D cup, you have a 3D cup, okay? And similarly, when you have a negative, if you recall, the second derivative test for one variable, if it is negative, you got a frowning face. This is concave downward. Okay, so the same concept applies here. Okay, the same concept applies. And if we have, remember last time, if equal to zero, the second derivative test for one variable, basically the test fails. Okay, the test fails. So if this is it equal to zero for 3D, this is what we call as the saddle point. The saddle point, because it looks like a saddle that we put behind the horseback. Okay, behind the horseback or behind the camelback. Okay, it is called a saddle point because if you look from one point of view, okay, look at the blue line, this is a local minimum. But when you look from this side, from the y's perspective, it is a local maximum. From the x perspective, it is a local minimum. So that's why it is called a saddle point where the test failed. The second derivative test failed, and we cannot basically come up with any conclusion. And that's it for this section. I'm going to end this here. All other parts of the lecture slides will be for your own, exploration. You can check on them. And yep, that's it for now. And I'm gonna make a few other videos to show the application of this multivariable calculus, inshallah. Thank you. Assalamualaikum warahmatullahi wabarakatuh.